Manuel?
Yeah.
Okay.
Yes, it is.
Okay, so start the session. So I'm Christian Kadar from Imperial College London in the UK, and I'm the session chair for this interesting session on reliability and safety. We're going to have in the beginning presentations of 5 minutes from each of the 6 papers presented in this session, and then we're going to have for half an hour discussions, and everybody can ask questions during this time. So we're going to start with Zhao Cheng Liu, who's going to who's going to no, we're going to start with Juyeon Yoon. Sorry, for some reason my spreadsheet was I was looking at the wrong thing. Who's going to speak about automatically identifying shared root causes of text breakages in SAP HANA 2. So looking forward to the talk, Jiyoung.
Okay, I'll share my screen. I guess everything is fine now. So today
Yes.
I'll present, yeah, okay. Today I'll present our paper, Automatically Identifying Shared Root Causes of Test Breakages in SAP HANA. This work is collaboration with KAIST and SAP Labs Korea. So let me start with explaining the post-submit testing process in SAP. The test run is performed on a daily basis in SAP and with all code changes together. And after the test breakages are identified, a bug ticket is manually assigned to each breakage. But the manual labeling can result in redundant bug tickets, causing unnecessary review effort. We propose a technique to identify shared root causes and merge the duplicated bug tickets. So, how can we know if two breakages share a root cause? The main assumption behind our approach is like the more similar two tests are, the more likely they are to share a root cause. And the next question would be, how can we measure the similarity between the test cases? We choose to use different types of information and calculate the similarity between the processed information, which are from 3 categories: static, historical, and dynamic. As static information, we use the test case names. We can either use normalized edit distance or measure the cosine similarity between the vector representations. To process historical information, we extract binary vectors from the execution history. We use both the fail and pass test results and the transitions in test results. As dynamic information, we use the test case coverage. Diverse similarity metrics can be used, but we additionally adopt hypergraph-based similarity. By this, we aim to compare the root causes between the failing tests in a more effective way. Our experiment uses 27 similarity function configurations, and we collected 6 months of test results. The data from the first 3 months were used as training dataset, and the data from the later 3 months test dataset. And we first compared the effectiveness of each similarity function. The effectiveness could be measured using the average precision, which can be obtained by the area under the precision recall curve. So based on the AP score, we found the best configuration for each information source. In the actual classification scenario, we need to set a fixed similarity threshold. However, the learned thresholds from the training data do not generalize well to the test data with any of the similarity functions. And if we compare the similarity functions, They are in fact complementary to each other. So we can now think of using all information sources together. To do this, we train a classification model that accepts all the similarity values and predicts the binary labels indicating whether the two tests share the root cause or not. We also confirm that the classification model outperforms all single similarity functions by a large margin. Among various model configurations, the combination of PCA feature extraction and Bagging ensemble model was the best performing one. Okay, so to conclude our talk, we first revisit our aim to reduce the redundant bug tickets by identifying the shared root cause of test breakage. And there were 3 types of usable information to represent the failing tests. Then, we propose a classification model integrating various similarity functions. Finally, we evaluate our technique on the test history collected from SAP HANA. And thank you for your attention, and I'll be happy to further discuss about our paper.
Thank you very much, and thank you for being on time as well. So next from the talk from Zhang Chao on record and replay of online traffic for microservices.
Yeah. So can you see me?
Yes.
Yes. So I'm from Ant Group. I'm going to talk about the record and play of online traffic for microservices with automatic mocking point identification. So what is record and replay? So record and replay is to record the online traffic and save them as the test cases, and then used for regression testing on the same software. Actually, in our company, it's microservices. But the difficulty is that on microservices, there are many threads, and so it's hard to repeat the same traffic, exactly the same traffic online and offline because of some state dependency. We classified this data dependency into 3 categories. First, the internal state dependency, like static variables. Then their values can range from in the online environment and the offline environment. And the external state dependency is the like the microservice. It calls other microservices like remote procedure call, and they also have system state dependency like the date and the random numbers. It reads some system values that can range at different times. So even the software or the microservice doesn't change. You may not replace the same traffic the environment to the offline environment. So the solution to this is mocking. So you not only record the input and output of the online microservices, but also some functions like this remote procedure call. You also record the input and output of it, and then you in the offline environment you mock this function with the recorded input and output. So here is the architecture of this system. But first, we need to take here is that we should have the mocking points before we put it on in the online environment. Before we do the recording. But there are some challenges. The biggest challenge is that we in the online environment we cannot have many mocking points as we wish, because if we too many mocking points will affect the performance, which will affect the user experience. This is not allowed in the company. So there are 3 challenges. The first is that we need to fund all the mocking points. The second is that we only allow AOP level recording because we cannot do a very high level injection in the online environment. The other challenge is the performance. We should have as few unlocking points as possible. So our solution is that we identify all these city dependencies, and then we find locking points through all these dependencies via Tensor analysis. And then we have some techniques to minimize the scope of locking points. So here I will not go to details of this dependency, but this dependency is immutable, which means we can find all of them. There is just some examples of them. Like the internal state dependency is like the Java beans and the static variables. Okay, here is the external, like the RPC, the proximal calls. But we found that mocking points they cannot be mocked directly like the new date. So we do tensor analysis to find the real mocking points. So I will not go to details of this, but we have implemented a lightweight tensor analyzer to do this. So I will not go to the details of this tensor analyzer. So this is a small example that we from a random system function that we can find two mocking points. The first is that both methods can be affected by the random value. So I will not go to the details of it, but so this is the effect of our work. We have deployed our methods as a microservice. It has served more than 200 applications inside Ant Group, and it helped find more than 90,000 mocking points, and with precision more than 97%, and the recall rate more than 98%. And the conclusion that about the performance, we only have with our mocking points, we only have less than 20% performance loss in the production environment, and it's used by the QA teams in Ant Group. Okay, thank you.
Thank you very much for the talk. Let's move to the next one by Cheng Shi on deep TRELog, on trace log combined microservice anomaly detection.
Okay, I'll share my screen. Wait, does it work?
Not yet.
I'll try again.
Okay.
Okay.
Yes, now we can see your screen.
Oh, okay. Okay, hello everyone. I'm Chen Xizhang from Fudan University in China. It's my great honor to be here to present our paper, Deep TRELog, trace log combined microservice anomaly detection through graph-based deep learning. As we know, microservice architecture has been the latest trend in building cloud-native applications. And in industrial, microservice systems usually have complex dependencies and changes frequently. So running in a highly uncertain and dynamic environment, microservice systems often fail due to various reasons. So the reliability is highly demanded in modern microservice system, and how to comprehensively and precisely detect anomalies has brought about widespread attention. The trace and the log have been widely used in anomaly detection for distributed systems. The existing anomaly detection approaches treat a trace as a sequence of series invocation, and treat a log as a sequence of log events. And most of them use deep learning methods to learn patterns from the normal execution and detect anomalies. Although there exist some approaches that do not handle the problem of microservice anomaly detection well. First, we found that the current approaches only make use of traces or logs. But in the microservice systems, trace and log describe different system behavior. As shown in the figure, this trace describes the service interaction for the request, and the log messages in each span record the internal states and the behaviors of the invoked service instance. So traces and logs can be combined for analyzing the runtime behavior of the microservice system. On the other hand, sequence-based representation cannot reflect the relationship between logs and traces. This is because asynchronous invocations and parallel invocations are widely used in microservice system. As shown in the figure, we can see the sequence-based representation cannot reflect the crucial relationship and between the parent and children span, and the temporal relationship between log events of the same spans. So the log events of different spans of a trace need to be combined in a way that the structure of the trace can be kept. To address the mentioned challenges, we propose the deep tree log. The core idea of deep tree log is that first we parse the span of a trace into span events, which are special kind of events that represent the start and the end of a service invocation. Then we use a graph-based representation to describe the structure of a trace together with the log events. This is the overview of the deep tree log. It includes 6 steps. We can see the first 2 steps are log parsing and trace parsing. In these steps, we parse log events and trace event parse log and trace into log event and span event. And then we use glue and TF-IDF to embed span events and log events into event vectors. And we construct the trace event graph for each trace to represent the relationships between the span and the log events of the trace. And finally, we train a guided graph neural network-based DeepFi3DD model, which learn a latent representation for each graph and minimize the hypersphere that includes the representation of the graphs in the training site. So in online anomaly detection, the traces outside the hypersphere are determined as anomalous. And this slide shows an example of the trace event graph. We can see the log events and span events in the same span form a sequence by their timestamp. And the events of different spans are connected via the request or response relationships between the span events. And to evaluate deep tree log, we use the benchmark system TrainTicket. It is a medium-scale open-source microservice system and has been widely used. And we use fault injection to produce anomaly traces. As shown in the table, our dataset contains 14 fault cases of 4 fault types. And each fault case may include multiple fault instances in different services. And we have open sourced our dataset in GitHub. And this table shows the effectiveness of deep tree log and other baseline approaches. We can find that the deep tree log achieve a high precision and recall in our dataset, and outperforming the baseline approaches, average increase of 0.37 in F1 score. And we also evaluate the efficiency and the impact of some key parameters of in deep tree log. And more details of the evaluation can be found in our paper. Here comes to the end of our presentation. Thank you very much.
Thank you very much as well. So we're going to move to the 4th talk now from Jan, who's going to tell us about decomposing software verification into off-the-shelf components.
Hi, everyone. Thanks for the introduction. So this is the idea of decomposing software verification into off-the-shelf components is joint work with Dirk by and Thomas Lemberger from LMU and my supervisor Heike Wehrheim. And as the title already suggests, we have software verification and we want to decompose that and apply this to SIGA. So let's start with what is SIGA. Firstly, the idea of the classical SIGA is roughly it contains 3 parts. So we want to verify that this task does not contain a bug, so to say, or we want to verify that. So the first part that is in the classical SIGA is to have an abstract model exploration, which takes the program and the property and then builds an abstract model of that, which, for instance, could be taking predicates and then check whether a certain predicate holds at a certain program location. And this abstraction is in the beginning really coarse. And hence, it is quite likely that we will find a counterexample in that first part. And this potential counterexample is then given to the feasibility check, because as we are working on an abstraction of the program, it cannot be guaranteed just the counterexample that we found is really an counterexample. So we need to check its feasibility. And if we found that the counterexample is infeasible, we are done. And if we have an infeasible counterexample, then we know, okay, our abstraction was too coarse and we need to refine the abstraction, which is done in the third step, which is the precision refinement step, which computes a precision increment. It gives this to the abstract model explorer, which then reads the full cycle. So that's a widely used schema. So many flavors of SIGA exist in the world of software verification, and nearly every time this is implemented in a stateful manner. And the problem if you have implemented this in a stateful manner is that you cannot just simply replace, for instance, the precision refiner part by something else without changing the full code. Or even worse, if you just have a nice idea for precision refinement part, you have to build the full tool, but you don't need it. So what we want to do in this work, and what we did, we want to decompose that into loosely coupled components, which are then can work standalone. So that's what we did. Now this is changed a little bit. We now see that we, on the one hand, have three components which have clearly defined interfaces. And these interfaces are violation witness, path witness, and invariant witness, and they are specified in a GraphML XML exchange format, so you can really exchange them between tools. And the three components are now abstract model exploration, feasibility check, and precision refinement. So why is this good? As announced and motivated, you now can easily exchange, for instance, a precision refinement. Let's say in the first you use a technique called Craig interpolation and you want to replace that, then you can use just use any off-the-shelf component that implements a different technique, for instance, Newton refinement, and then just simply exchange it and run everything without a lot of work. So in fact, it's changing 2 lines of code. And that's mostly due to the implementation which we did in a tool called Coverity that was published recently, which allows building that framework. But this work just contains the conceptual idea. And of course, we checked, does it work out? Is it a good idea? And we had a look on 3 different questions. First, what is the overhead? So if you take an existing schema, which is stateful, and break it into 3 components, the question is, does it pay off, or does everything breaks down? And we found out that the effectiveness is not really influenced, so only by a small margin. But the efficiency decreased around 3, which is not surprisingly because we changed from stateful to stateless components and have exchange formats which need to be read and read. If you use standardized formats as here, then the effectiveness reduces by a factor of around 20% due to some informations that are not correctly encoded into that format. But the efficiency is in this case not influenced. And as a last, we realized if you use different components, which was the motivation behind this work, then this really pays off because you can solve more tasks. So if you, for instance, replace the precision refinement by something else, this pays off. So to sum up, what does SIGA do? It breaks the tightly coupled SIGA schema into small standalone components. And we showed that on the one hand, it has a similar effectiveness as the tightly coupled one, and that different techniques which exist and can be used off the shelf improve the effectiveness. So as a take-home message, I just can say decomposition is possible and worth it. Just try it. For trying, we provided an artifact which is reusable, and you can find it in this link. It is also linked in the on the website and in the small teaser. So if you want to play around with that, try it on your own, implement your own tools. That's easily possible now. Thanks for your attention. I'm happy to answer questions.
Thank you, Jan. We're now going to move to the 5th talk from Ion on precise division by zero detection with affirmative evidence.
Okay, let me share my screen. Sorry. Sorry about that.
Not yet, but it worked just fine when we tried it just before the session.
Okay, can you see my screen now?
Yes.
Oh, okay. Hello, everyone. My name is Yiyuan Guo. I'm happy here to share our recent research on precise divide-by-zero detection. A divide-by-zero is a common programming error when you perform a division instruction with a zero divisor and can lead to undefined behaviors such as crashing the system. Over the past 5 years, there are more than 90 CVEs related to divide-by-zero bugs. There are many approaches to combat the divide-by-zero problem, including dynamic analysis and static analysis. In this talk, I will focus on the precise static detection of divide-by-zero bugs. The motivation of our work comes from our experience in deploying representative static analyzers in catching divide-by-zero bugs. We observe a high false positive rate of over 70%. So the question is, why is this unsatisfying precision? Conventionally, static analyzer finds a divide-by-zero bug by finding an execution path that ends in a division instruction. Then the static analyzer can encode the path condition of this path into PC and conjunct it with the error condition for the divisor to be 0 to formulate the final constraint. If this final constraint is satisfiable, the static analyzer chooses to report a divide-by-zero bug. However, in real-world programs, there are many unknown factors to static analysis. For example, the value of V may come from some unmodeled library calls. The computation of V may involve some complex language features such as inline assembly. When such cases happen, the variable can be under constraint in static analysis. And when such under constraint variables appear in our final constraint, it can lead to massive false positives. The key insight of our work is to attack the divide-by-zero detection problem from a different angle. Instead of reporting a bug whenever safety verification fails, we can try to actively find affirmative evidence for triggering divide-by-zero bugs. Here, evidence means extra information on under-constraint variables, which can contribute to improving the precision. Let me use an example for illustration. For the 3 functions shown here, the variables x, y, and z are all under constraint in static analysis. Also, notice that the path conditions for these functions cannot rule out the possibility for triggering divide-by-zero bugs. Therefore, in the eye of a conventional static analyzer, it will regard all these functions as susceptible to divide-by-zero. However, our approach will only consider the middle program and the right program as potentially able to trigger divide-by-zero bugs. For the middle program, we can observe that the programmer explicitly compares the variable x against y. This suggests her beliefs that x can equal y. When such beliefs actually hold, x minus y must be 0, so there is a divide-by-zero bug at the return statement. For the right program, since x comes from some tainted input, it may take any value, including the 0 value. So there is also a good chance for the right program to trigger a divide-by-zero bugs. More specifically, we say that we have found bound evidence x equal y for the numerical comparison statement in the middle program, and we have identified source evidence for x to be tainted from the right program. And our approach will only detect bugs which have some evidence discovered. Through an empirical study of 87 CVEs caused by divide-by-zero bugs, we found out that 74% of them have evidence to support their bugginess. Therefore, our evidence-based idea do capture considerable real cases. Our approach is a path-sensitive evidence propagation algorithm. First, we will construct an augmented data dependence graph of the program, and we'll apply a guarded value set symbolic domain to represent the numerical relationships among variables. Then the 2 kinds of evidence is generated and propagated along the data dependence graph, and they are resolved, and we'll resolve a set of constraints of our symbolic domain to detect bugs with high confidence. We implement this idea in a tool called Breed based on LLVM, and we have found 14 confirmed bugs with a low false positive rate of 22%, significantly outperform existing static analyzers. That's all of my presentation, and I will be happy to take questions later.
Thank you very much, Yuan. And we're now moving to the sixth talk from Clarice on repairing brain-computer interfaces.
Okay, can you see my screen?
Yes.
Okay. Hi, my name is Clarice, and today I'll be sharing our work on testing and repairing brain-computer interfaces. Every year, millions of people are affected by spinal cord injury, limb amputations, and stroke, resulting in motor and sensory impairments. Brain-computer interfaces, BCIs for short, offer a promising solution for these individuals. BCIs provide an interface for communication between the brain and hardware, and thus can be used to restore movement and sensation. Many BCIs first record signals from the brain, then utilize a neural decoding model to infer an individual's intended action from these recorded signals, and finally control a hardware device to perform the intended action. For example, consider a hand prosthetic, which is a BCI that can restore hand movement. This device continuously records signals from the user brain, and when the user thinks of performing a certain task, such as making a fist with their left hand, the neural decoding model uses the recorded brain signals to infer this intended task. The prosthetic then responds by performing the task by controlling the posture of an external hand prosthetic device. Because BCIs operate in scenarios that are highly safety critical and require precision, it is important that even the smallest mistakes or faults are eliminated. Current methods for BCI fault repair involve time-consuming recalibration sessions, where a clinician asks the user to imagine or execute tasks that the BCI is expected to perform, such as holding various hand postures, while brain signals are recorded. This data is then used for model retraining. However, this process may be ineffective for repairing faults. It does not prioritize tasks for which the BCI currently performs work on. In our work, we explored how to effectively test and repair BCIs by thinking about the underlying neural decoding model as software to be tested. We propose a human-in-the-loop methodology for testing faulty BCIs and repairing them by accounting for actual detected faults. First, BCI faults are automatically identified via expert-defined partial test oracles. These oracles can detect noise artifacts in the recorded brain signal inputs, temporal validation faults, such as invalid transitions between different output states, faults in which a model output is inconsistent with the output error-related model that accepts auxiliary data, and faults based on domain knowledge. Once faults are identified, fault localization is used to produce a fault-based task distribution. More specifically, we localize faults to tasks and input slices to understand the co-occurrence of each fault with each task that the BCI can perform. Finally, this task distribution is used to guide data acquisition in a recalibration session, as the clinician can now focus on tasks that co-occurred with the BCI's faults at higher frequency. The resulting training data that the model is retrained on is thus weighted more heavily on the tasks that the BCI had a hard time performing well on. We evaluated this methodology on 5 BCI applications, with models trained on open source datasets. The selected BCIs varied in their inputs, outputs, use cases, and neural decoder models. By applying partial test oracles to test BCIs, we found that a non-trivial number of faults do occur, and that partial test oracles detect faults that are indeed incorrect model predictions. We found that these detected faults localize the tasks and input slices. Finally, we found that repairing BCIs by retraining the neural decoding model on training data acquired based on this fault-based task distribution lowers the fault frequency in some applications, and overall does not impair the model performance. Our work demonstrates that an expert-in-the-loop methodology based on partial test oracles and fault localization is an effective way to test and repair BCIs. There are many avenues for future work. such as testing BCIs in more realistic settings, applying this methodology to other machine learning-based biomedical systems, and exploring how to test the programmatic system itself. In conclusion, we were excited about the prospect of future research in the intersection of software testing and brain-computer interfaces, and we believe that the application of software testing can increase safety and trust in BCIs. I am grateful to my co-authors for their collaboration, the ICSE coordinators and chairs for organizing this event, and thank you for listening.
Thank you, Clarice, and thanks to everyone for a set of very interesting talks. Thank you. So now we have 25 minutes for discussion. So I certainly have a number of questions across talks, but I would like to give others the opportunity first to ask. So you can raise your hand, I believe, or you can just speak, or yeah, I mean, we can be flexible. And obviously, the speakers themselves, you know, should ask questions. So, who'd like to go first?
I would like to ask a question for Junyuan. I noticed that there are 3 types of information sources for the test breakage problem. Do you, for example, evaluate which part, for example, is more important for the overall performance, or these 3 parts of information source contribute evenly?
Oh yes, that's actually our first research question, and we both quantitatively and qualitatively evaluated the effectiveness of each similarity function belonging to each information source category. So,
okay.
But yeah.
I guess as a follow-up to that, so the sources of information that you determine, how specific were they to your application? So how much would they generalize? You know, if you wanted to try a different application, for instance.
You mean the different data set? Or
yes, a different application, right? So I think that you're looking at SAP HANA 2, right? Let's say that you wanted to look at a completely different application. So which things would generalize, which things would you have to tweak, you know, for the approach to work well, for these test breakages to be
yeah, for this work we mainly concentrated on our target data set because it has the ground truth label labeled by the actual developers, but in other open source data set, it is hard to get the actual label of actual labels of the same root code. Yeah, with the same root codes, and actually our previous work about modeling the coverage with hypergraph, we used defect4j, and we in that paper we artificially combined the fault in defect4j and evaluated on our hypergraph-based approach on that. But this paper doesn't consider multiple information sources. And maybe we can verify our approach on those data sets as well.
Okay, thank you for the question. As a reminder, if somebody wants to ask questions also on chat, that's also a possibility.
Yes, I also have a question on Julian. So so compared to, I mean, on the same application on the same data site, so how long does it take for a programmer or developer to have such data that for developer to find the root cause?
So you mean the
I
the
mean,
time
how
cost?
yeah. So the time cost for a developer is something else. I mean, if you pay manual work on it, how long does it take? I mean, I think this defines how complex how complex such breakage is.
Yeah, for the manual work or for our
Yeah, yeah.
model? Manual work?
Yeah, I mean for your data set, I mean for your application, I mean if
Yep.
some breakage happens,
Mhm.
on your data set, do you have data that how long does it take for the developers to find the root cause?
Well, maybe for the actual developer, actual cost of developer to find to identifying the root cause, we haven't surveyed about for the developers because we didn't do user survey in our work, but definitely that's a valuable direction to explore. But yeah, in our data set, we identified there are plenty of duplicated bug tickets, although those breakages have the same root cause and should have single bug ticket. So yeah, we identified the problem.
All right, so let's move to some other paper as well. So maybe I can ask you, Zheng Chao. I was curious. You mentioned like this 90K identifying points, and you mentioned like 2.5K false positives, 1.6K false negatives. My question is, how did you determine this? Was it like a manual analysis? And second related question, what's their impact? I mean, perhaps like percentage-wise might be low, but still seems like a very large number of false positives.
Okay, that's a very good question. Actually, the first thing that how do we measure the precision and the recall? Actually, all our generated mocking points are used to the recording process, and after the recording process, if some test case fails, then we know we have missed some mocking points, and also the developers will also check our mocking points whether our mocking points, fulfill their requirements. So actually, every mocking points are checked by the developers, even the 90,000 mocking points. But that's from.
This seems like a lot of work, right? Or is it semi-automatic?
Yes, it's a lot of work. Actually, but they are from 200 microservices. Around 200, so there are maybe I think there are at least more than 200 developers behind it. Actually, before our work, they do this manually. They manually find the mocking points. It will take them maybe weeks to do that. So ever to actually reduce the weeks of manual work to maybe minutes of work, and then they check. And because the high precision and high recall, the time they spend maybe only within 1 day sometimes.
Okay.
Yeah.
Thank you very much. Let me also draw your attention again to the chat. So Xinyu added a clarification about the first paper that I encourage people to read. So let me go, on this note of, false positives, false negatives. So if I can ask Yuan a question on his technique. So that's a very high-level question, but I wanted to. I mean, obviously, by having this precise division by zero detection, you increase the false negative rate, right? So, what do you think of this trade-off, right, between the false positive and false negatives? with respect to your approach and in general to division, detection of division by zero errors?
Yeah. This is a trade-off of negatives. Actually, in the paper, existing divide by zeros, and we found that 74% of them can be captured by this evidence-based idea. So there's some empirical confidence to apply this method. That in bug detection, we favor precision over recall because this is not sound in an over-approximate idea, but we try to find a portion of high confidence bugs. However, it cannot be formally proved that what are the bugs that are missed. So it can be shown from the evaluation and experiments that these detected bugs are more close to those true bugs.
All right, thank you. That's I think that's a very interesting design point. Thanks for your comments on that. Can I encourage the audience or the speakers to ask more questions? All right, Jan.
So I had a follow-up on that question, so on that topic. You said that you're searching for evidence. What kind of evidence are you searching for? So in the talk, you just motivated that with this X is greater or equal to Y. Are there any other kinds of evidence that you are working with? And how did you, specify that?
This for the evidence in our work, it's all automatic, right? We do not need to write specification for functions. Motivation is actually from previous work that we look for how the variables are used to infer some properties of them. So in this paper, we just use one simple property that if you compare two numerical variables, then I can say those two compared variables may be equal. And if you do not rule out this possibility in your past condition, then I will treat it as a fact of high confidence. So that's the main evidence we use in this work. Actually, there are not very much you can tell without manual specification. You have to infer from how these variables are used locally and try to discover some interesting facts that we use in this paper.
Thank you.
Anyone else? If not, let me ask quickly Jan a question. So how, I was wondering, so obviously this seems like really nice to be able to decompose the software verification tasks into components, right? Very useful in many ways. But how hard is it to extract such components from existing tools? Have you looked at that?
Yes, so you can. So for some of these subtasks, especially for the feasibility check, you just can use existing tools. So this is a task that is done by lot tools because this is just, here's a pass, is this really a violation or not? And the competitions that are around, this is called, for instance, a violation witness validation. So there are, I guess, 12 or 15 tools which already does that, and you just can use them. For the other tools, it's a little bit harder. It depends. So some allows easy decomposition because you can configure it in such a way that you say, okay, I just want to do it like this or that, and just this subtask. But for some tools, it's definitely a little bit harder. But for a lot of tools, you just can use them off the shelf without doing any work, any configuration work, to be precise.
And I was also wondering if you can explain again what are the main sources for the efficiency decrease. You said you see a constant factor. Is it because of your exchange format, or because it's not in, things are not in memory anymore, or what?
Yeah. So it takes longer. So that's what we see in the one hand, and hence if we evaluated these tasks with a fixed timeout. And if we increase the timeout, then we can say, okay, if we just, in the paper, we increase the timeout by the factor of 12. And then we see, okay, we can only solve just a few tasks. They are not solvable because some solver issues occurred, but we can solve all the tasks. It takes longer because of the separation of the statelessness, and as we have to read and write the exchange formats, which just takes some time.
Okay, thank you.
Yeah.
All right. Can I also encourage some questions for, so we haven't got a chance to talk about the paper on anomaly detection, deep trilog, and also repairing brain-computer interfaces. Any questions on those papers?
Yes. For Chen Xi, I would like to ask, how do you construct the trace event graph? Is it constructed from static analysis, or it is recovered from the trace log?
You mean how we construct the graph?
Have a trace event graph, right?
Yeah.
For representing the relationships of all these microservices.
Yeah.
So is it a static analysis or from the collected dynamic logs?
We construct the graph by collect the dynamic information. We use a distributed tracing twice to collect the trace, and we print the trace ID and spam ID to the log messages. So we can connect the log message and to the specific request to the trace, and we parsing it to the event and depend on the timestamp and the children or parent span relationship to construct the graph. We don't use some static analysis tools.
Okay.
So I guess as a follow-up to that, I had a very similar question. So yeah, it wasn't very clear to me how this is constructed. So you're saying that for two different executions, because of non-determinism, of course, you have like this all these asynchronous invocations. You may end up with different graphs, right?
You mean different invocations? Asynchronous or synchronous?
No. Okay. So I'm saying because you're using the dynamic traces, right? If I understand correctly, from what you answered to Yuan, let's say that I execute the program twice. All right. I execute it 2 times, so there is some non-determinism there, right? Let's say that events now come in slightly different at slightly different times. You may end up with different graphs, right?
Yeah.
Okay. I understand. So have you thought about combining this with some static analysis to try to be more complete with regard to your analysis?
Yeah, we have thought it, but we have not done it. Maybe in the future.
All right. Thank you. And any questions for Clarisse? So that's certainly very new topic, very interesting one. So I was curious to ask, it wasn't clear to me immediately where your benchmarks, where the data came from. Can you comment a bit on that?
Yeah, so these are from open source data sets. So typically researchers perform experiments with patients and collect neural data that's mapped to certain tasks. And then there are multiple open source data sets that we used for our work.
Okay, I see. So you didn't use one of these devices. You didn't experiment with that. There are existing data sets that you can reuse. So what you mentioned, like the possibility of looking beyond these devices. Is data acquiring data a challenge, or is it like widely available and something that people can already freely study if they're interested?
Yeah, so there were multiple open source data sets that people have already collected. It's not always easy to set up your own experiment and get a bunch of participants and record data ourselves. So that's why we kind of went about just using open source data sets. One avenue for future work would be working with more types of brain-computer interfaces and different types of neural recording modalities and things like that. So yeah.
Okay, very interesting domain. Okay, so we have 5 more minutes in the session. So any other questions for anyone? I think we covered all the papers with a couple of questions, but any bonus questions?
I have a question about the paper of automatic mocking point identification in microservice. So maybe I didn't fully understand your technique, but I wonder about the case of nested library calls, because if the library call contains contains some state dependency, so and if it is nested, I think the problem gets severe. So how do you handle that?
Yeah. Actually, that's a very good question. I didn't mention that in our in my slides, but it's mentioned in the paper. Actually, there are some what we call third-party libraries with like they read some system or state like time handling or random number handling. There's only one way to deal with it is we add some whitelist on these third-party libraries. Yeah, we don't do analysis on the we don't do static analysis on the library code. But fortunately, there aren't many such libraries. So in each application or microservices, there are at most 3 or 4. I mean, there won't be many, so it's okay. Yeah, compared to the hundreds of mocking points from the application code. So the mocking points from third-party libraries are not many, so it's okay.
I see. So for the follow-up question, could you? I think it can be also applied to the general mocking point identification other than microservices, but maybe that point library thing can be a challenge for the generalization. But do you think that's possible?
I think that it's possible, but I think the popular libraries aren't so many. So and if especially in the company, we only use some selected libraries. So I mean I don't know other companies, but in our company we there aren't many. So but in other companies or in other domains, that may be a problem, I think.
Okay, any other questions?
Yes, I have a question here. So can you hear me?
Yes, we can.
Okay, good. So I have a question about log work. Yeah. Actually, I have a question about how do you connect the trace log and the system or microservice log? Because if you only look at the time step, that time step might be not so accurate, and there might be some you cannot the time resolution is not so accurate. So I'm wondering, do you apply any other label for connect the span event and its corresponding log segment?
Yeah, we use the distributed trace skywalking to print the span ID and the log trace ID to the log messages, so we can connect the log message to the specific request. And
okay.
Yeah, we connect the and the log and the span event in the same service, same invocation, and their timestamp may be accurate, so we can connect it. And the different spans we connect it by the parent and children relationships. Yeah.
Okay,
so,
thank you.
Okay. Yeah.
Okay. Time perhaps just for a very quick question. If there is such question. If not, I propose to wrap up because we have only a few more seconds to go, and I want you to be able to join other sessions on time. So thanks everyone for interesting talks, interesting discussions. I think the format worked quite well, and best of luck with your future work.
Thank
Bye,
you,
everyone.
Chair. Yeah.
Bye-bye.
Bye. Thank you.
Bye-bye. Thank you.
Bye.